Okay, let's add some specific processes of the climate system and Earth system. I'm going to use these interchangeably because the course itself is on introduction to climate science, climate change, and climate modeling, but we will use Earth system and climate system interchangeably. Here are some examples of determining the climate with their characteristic time and spatial scales, temporal and spatial scales. So the component of the climate system, atmosphere, process, characteristic time scale, and characteristic spatial scale. So just try to imagine you're trying to model the global climate and you're starting at collision of droplets during cloud formation, literally at molecular scale. So these scales characteristically in time are 10 to the minus 6 to 10 to the minus 3 seconds. So we are talking about climate at seasonal, interannual, decadal, multi-decadal time scales, and we're talking about processes at microseconds and nanoseconds, milliseconds and microseconds. Characteristic spatial scales of these cloud droplets happen at 10 to the minus 6 meters or micrometers. Okay, so just imagine trying to model those. Formation of convection cells in the atmosphere when hot air rises with the moisture, expands, cools, forms clouds and rains. That happens at 10 to the 4 to 10 to the 5 seconds. So you can see the range of time scale here going from 10 to the minus 6 to 10 to the 5. Boom! 11 orders of magnitudes. Characteristic spatial scales, 100 meters to a kilometer. 10 to the 4 meter is 10 kilometer. Development of large-scale weather systems happen on 10 to the 4 to 10 to the 5 seconds, so hours to days, and happen on basically regional to planetary scales. Persistence of pressure distributions, 10 to the 6 seconds, days to 10 to the 6 to 10 to the 7 meters. Very large scale pressure distribution patterns happen. Southern oscillation, which we have learned as El Nino, which we will again visit a little bit, and I have podcasts and lectures on this topic you can look up. Basically it's the oscillation of sea level pressure between Darwin and Tahiti, which corresponds to the zonal circulation in the Pacific, with upwelling and cold temperatures in the east around Galapagos, warm temperatures in the west around New Guinea, Australia, and this oscillates on interannual timescales. That means longer than a year, so it happens every 2 to 7 years. Happens on 10 to the 7 seconds, so that corresponds to the time scale we're talking about, and 10 to the 7 meters, which is the scale of the Pacific and the globe, in fact. Troposphere stratosphere exchanges, looking at the vertical, 10 to the 7 to 10 to the 8 seconds, and this is global in spatial scale. So here I said global, so maybe it's better to say planetary, because that's where Coriolis becomes important enough, and global is really global. Okay, hydrosphere, gas exchange, atmosphere, ocean, again very short time scales and can be at very small spatial scales. The correlation and covariance of turbulence, which determines the exchange, can be at that turbulence scale or molecular scale. Deep water formation happens on very long time scales and very large, relatively large spatial scales. We will see, we have seen already that deep water formation happens in the North Atlantic, Ross Sea, Weddell Sea, and so on, so they are regional scales. Mesoscale oceanic gyres. Meso is kind of the very catch-all word sometimes, but let's not get into it. These are in the range of 10 to the 6 to 10 to the 7 seconds in time scale, 10 to the 4 to 10 to the 5 meters in spatial scale. These are the subtropical gyres, where the trade winds and the mid-latitude westerlies together create clockwise circulation in the northern hemisphere counterclockwise circulation, in the southern hemisphere where waters converge and sink, so in the subpolar gyre it's the other way. Propagation of Raspy waves. We haven't defined what Raspy waves are, but basically if you imagine the sphere, the Coriolis is 0 on the equator, increases with latitude. So if you displace air parcel, then you change its Coriolis effect on it, or its vorticity. So to conserve vorticity, it will want to come back, it overshoots and then goes back. So you have a perturbation force and a restoring force, which is what generates waves. So we will see an example in the jet stream of how Raspy waves occur at the time scale of 10 to the 7 second and the spatial scale of 10 to the 7 meter. El Nino southern oscillation closely related, 10 to the 7 to 10 to the 8 second, 10 to the 7 meters. Turnover of deep water is a long scale process, so you can see in the whole table this is the longest time scale, can take centuries to thousands of years for the water to sink and then get converted back to surface water and come back to the region of sinking again. This is obviously a global thing. Cryosphere, formation of permafrost, 10 to the 7 to 10 to the 9 second, 1 to 10 to the 6 meters, so can be very small meter scale to large regional scales. Formation of sea ice, similar. Formation of land ice masses or buildup of glaciers takes a very long time now, longer than the deep water time scale, because as you build glaciers, reflectivity albedo goes up and temperatures cool down, which means, remember your Clausius-Clapeyron, amount of water in the atmosphere reduces, which means the snowfall rates reduce, which means the glacier grows slower and slower. So we will see that in a minute in terms of the non-linearity of the melting phase of the glacier and the build-up phase of the glacier, which we have briefly mentioned before in the context of ice albedo feedback. So that's can be 100 meters to global, so you can have little mountain glaciers in Himalayas which are order 100 meter or smaller even, and of course you have global scale glaciation possible. Isostatic equilibration of the crust by covering ice masses. So when glacier grows, so much weight is put on the plate that it can be pushed down, and that can happen on 10 to the 8 to 10 to the 11, so similar to the formation of land ice masses, and can be 10 to the 6 meters, so 1000 kilometers to global. Biosphere, exchange of carbon with the atmosphere. Here are the time scales, and can be very small scale to global scale. Transformation of vegetation zones, for example with global warming. How are ecosystems changing? How are tropical forests changing? Temperate boreal tundras, how are they responding? Can be slow time scale because the ecosystem equilibration time scale is very slow. And the spatial scales can be just 100 meters to large scale. Okay, so again, let me leave the scales in time and space here, so that we can come and start looking at what kind of details the models have to worry about based on their main goal. Whether it's prediction, process understanding, predictive understanding, or systems understanding, understanding the feedbacks, and so on and so forth. Okay.